Good morning. We are continuing lecture on how to start thinking in terms of wing loading for takeoff case, right? Wing loading for takeoff at conceptual stage. In last two lectures or so, I tried to build how to think to visualize what is wing loading as far as takeoff is concerned. We did mention about the forces acting and the approximations and how important it is for the airplane performance. We discussed about high lift devices which can reduce the takeoff length. We have discussed about thrust to weight ratio, which will also reduce takeoff length if I increase T by W. But you should also appreciate at a conceptual stage, we do not have all the parameters because we have not configured the whole airplane as it is. But we know one thing, whatever airplane I am conceptualizing, a similar aircraft of that performance will be available in the market. And we always select such an aircraft whose mission requirements are closer to what we are going to design, and we nomenclature them as baseline aircraft. So we pick some number from there and try to get some value for W by S. There is another popular way is why don't you use statistical data exhaustively and get the feel for wing loading, all those parameters. Because after all, the aircraft which you are going to design will be part of the family of aircraft existing already. You are not doing something extraordinarily different, right? So in that direction, I will just use few of the guidance given by Raymer. I thought I will share with you. But before I share, let me also discuss how those charts are prepared, right? And you must appreciate the designer's insight, how much they might have put effort to get those charts in a manner which is based on the model, okay, not just a heuristic. So if I am talking about, let's say, loosely takeoff distance, although we know it rolls and climbs and this is the takeoff, let's say we are talking about this much ground roll distance. We understand one thing, that if I can somehow manage to approximate A as average acceleration, right, and neglect drag and lift contribution as compared to thrust, which we have done, then I can write A is equal to T by M, and I can simply use V square minus U square equal to 2AS and S equal to V square by 2A, where A is T by M. We also know this V, which is the final velocity here, it should be 1.1 times V stall as per one of the regulations. Be careful about it. These sort of numbers are very specific to different types of aircraft, it is civil or military, and these are guided by the regulatory bodies. So you have no option to change those. So now if I use this and we find that V stall is 2W by S by rho CL max, then I can easily see from here V takeoff will be 1.1 times 2 W by S rho CL max. But we also understand that since I am taking off at 1.1 times Vstall, this V takeoff is 1.1 times Vstall, and we need to understand the CL max is not CL max here what we are aware of, that is CL max corresponding to V stall, because V takeoff is 1.1 times V stall. So let me write V takeoff as 1.1 under root 2W by S rho CL takeoff. And if I do this, then I find S equal to 1.21. This becomes V takeoff, 2W by S, then rho CL takeoff into 2 into T by M. So these two and these two get cancelled. So I am left with S1, which I am telling this distance, S1 equal to 1.21 into 2 into W by S into G divided by rho CL takeoff into 2 into T by W. So watch out for the parameter W by S by rho CL takeoff into T by W. This will be proportional to W by S, CL takeoff, T by W, and rho proportional to S1 into some factor A, which A will be, you can find out from here. So important thing is, if I plot the ground roll distance and this parameter, they will form a straight line. Right? I can do different experiments, or I can take the data from different aircraft and fit the data using this model, right? And that is exactly has been done. If you see here, which I am referring to Remer's book, if you see this x-axis is takeoff parameter, where the takeoff parameter TOP is defined as W by S by sigma CL takeoff into T by W, or it is W by S by sigma CL takeoff into BHP by W. In a similar form, only in this we have seen there is a rho. Rho has been replaced by sigma to take the density effect, because sigma is nothing but density ratio, and is rho by rho naught. So they have given a lot of correlation between this parameter, which is called takeoff parameter, and the takeoff distance, which is essentially what we are referring there. And that's, for example, if you want to find out what wing loading I should have for a 7,000 feet takeoff length and for a jet aircraft, so I'll go like this, and jet here, I come down, it will be around 340 or 350, around that. That value will be takeoff parameter, will be around 350, which will be equated to W by S, sigma CL takeoff into T by W. This is clear? Depending upon what sort of a land roll distance you want, say 7,000, so pick 7,000 here. What type of engine you are using, jet engine, you found this point, come down and get what is the takeoff parameter number. Right? And once you get that number, you equate this with W by S, sigma CL takeoff into T by W. So takeoff parameter equal to W by S, sigma CL takeoff into T by W. This I have seen picked from historical data. My aim is to find out what is W by S. For takeoff, sigma is my control because depending upon what altitude I am taking off, so I know density at that altitude and I know density at sea level. So this is in my hand. Yes, the question comes, what is CL takeoff? And we'll now answer this since we know V takeoff is equal to 1.1 times V stall. Right? So CL takeoff automatically becomes CL max by 1.1 into 1.1. So this is equal to CL max by 1.21. So CL takeoff is also known. The question comes, what is the T by W values? Okay. Or for a designer, another question comes, what is the combination of W by S and T by W to meet this takeoff requirement? So that is where a designer perception is very, very important. So he will be looking for a similar baseline aircraft which belongs to the same or closer mission requirement. So he may initially pick, okay, T by W, I will take around 0.25 from historical data. Also, you know, T by W 0.25 means what? If T by W is 0.25, then you know that when I am climbing, then T minus D minus W sine gamma equal to 0. If I am doing steady climb, so T by W I know equal to sine gamma plus 1 by CL by CD roughly. And CL by CD, let's say you are around 15 or 10. If it is 10, this value is 0.1. So sine gamma will be equal to 0.15 if you have taken T by W equal to 0.25, and that will correspond to a particular climb angle. So you have to see, generally for normal aircraft we will prefer initial climb by 7 to 8 degrees. Okay? So all those things goes into your mind. And if you find doing this, the type of T by W I have selected, I am not able to really getting a realistic number for 1,000 feet or 6,000 feet land roll distance, then you can increase this. So this sort of a matching will or adjustment goes on. But this is how you can use the data given in Raymer, which is fairly useful, right? Okay. I thought I must complete that also. So that brings down the conclusion of W by S takeoff for conceptual design. Okay. Now we will also discuss about the landing distance. Landing distance first of all, let us visualize when I am taking off, I will be giving, let's say 50% of the maximum flap deflections. I am a little conservative in giving flap deflection more because more drag will be required, so more thrust weight will be required for takeoff, right? But while landing, you will find almost full flap deflections are given. The reason being there will be increment in CL max, but more importantly, there will be increment in the drag because you want to break it, right? Anyway, for the wing, there will be air brakes will come out, so CL max anyway that will be destroyed through the spoilers, right? So one thing we understand that CL max required or CL takeoff during is always less than CL landing. Okay? And that is more so because you want while landing, you want your touchdown velocity should be as low as possible. You land like this, you come for an approach, then start coming down a glide slope of around 3 degrees, flare up, touch, go like this, okay, apply brakes. At a conceptual stage, whatever takeoff distance you get, you add 15% more or even 50% more and your landing distance will be safe. But you need to know how the regulation dictate for safety point of view, FAR 23. I am giving very old FAR requirement. It says S-land in meter should be 0.35 VA square. This also I have been following NPTEL lecture by Professor Tula Purkar from IIT Madras. Right? You can always read that. And FAR, this is an FAR 25. This thing goes on modifications because of more and more the experience they get it, and they 455 VA square. And this is for civil, of course. And for military, land is around 0.3546 VA square. What is this VA? That is important. VA is approach speed. See, when you want to land, you come to the point nearer to airport, and you set a glide slope of 3 degrees, right? We talk to the ATC say, okay, now start. So with 3 degree glide slope, you start approaching the airstrip. Then you do flare and land, whatever it is. And if you see the regulations for civil, VA is 1.3 times V stall. Please note that whatever VA conditions I am giving there as per FAR 23 and 25, they are old. Now they have been modified, but it will be hovering around 1.2 and 1.3. Nothing. So you understand what is required. That's more important. And for military, when you say this here, VA is 1.2 times V stall, and for civil it is 1.3 times V stall. So you understand that if pilot is not maintaining this sort of a conditions, right, during landing, it can lead to an accident. If it is lower than this speed, then the moment it flares up, it will go to a stall because it starts sinking. If it is higher, then while it lands, it will give a lot of impact to landing gear. So how important is these numbers, right? Okay. And it will be clearer when we actually solve an example. Please note down these things. These are important things for us. Yes, what we are looking for? We are looking for wing loading. So I write now W land by rho naught into sigma into SCL max. Please see the difference here. W land is W landing. So whatever weight with which you are taking off, when you come for landing, at least fuel is burnt. So the weight reduces. So W by S during landing is less than W by S during takeoff, right? Now here, instead of sigma, this is sigma rho naught into rho by rho naught, it is written. Both are same. And CL max, you know what is CL max. If this is agreeable, then I can write V or W by S landing. I just square it. It will be CL max into sigma into rho naught into VA by 1.3 square landing. Right? Because you know VA equal to 1.3 times VS. So VS will be VA by 1.3. So that has been done here. So if I further simplify it, it will become CL max into rho naught by 2 into sigma y 0.69, then S land by 0.3455. So this will be W by S landing. I hope you have understood how we have come from here to here. If the VA by 1.3 is clear, And also we know that SLand equal to 0.3546 into VA square. So that has been, so VA is SLand by 0.3455. That is exactly has been put here. So now life is simple. If I want W by S for landing, I need to know what is the land road distance I want. I need to know what is the sigma density ratio. I need to know what is CL max of the airplane I am designing. That's all. Okay? So this becomes very simple. So you have W by S. Takeoff, you will have now W by S. Landing, you will have W by S. Cruise, you have W by S. Climb, you have W by S. Loiter, and W by S for acceleration. You will find to meet all this requirement, you will have different wing loading. The challenge would be which one should I pick? Because if I pick any one of them, it may satisfy that condition, it may not satisfy other condition. So that is where the design optimization becomes important. Okay? And once we solve an example, then only we will be able to tell you, demonstrate a designer how he applies his mind, because whatever aircraft you are designing, you have to find out what is the main purpose of the airplane. If it is a transport airplane for carrying passenger from point A to point B, then naturally you will give more weightage to W by S cruise, right? If it is a fighter, dogfight airplane, then you will give more weightage to W by S acceleration. So all such things, or if it is a surveillance airplane, you may give more weightage to W by S loiter, right? It has to just move around. Endurance, more endurance. So all these things you have to see depending upon mission requirement and select the W by S. My next lecture will be on Man Ki Baat, that you know that, where I will be summarizing whatever you have done, so that we are now ready for designing an aircraft at least conceptual level, up to the wing loading and thrust loading. Thank you very much.